December 7th, 1941, Pearl Harbor, Oahu. The destruction of the USS Oklahoma was not just a sinking, it was a catastrophic failure of geometry. Most battleships hit by torpedoes will sink vertically, settling into the mud like a stone dropped in a pond. The Oklahoma did not settle. She performed a violent, lethal somersault. Just before 8 a.m., the first torpedo slammed into the portside anti-torpedo bulge. The engineering theory behind these blisters was sound. They were essentially hollow steel pillows designed to absorb the expanding gas of a warhead and protect the inner hull. But the Japanese Type 91 aerial torpedoes were not theoretical. They carried 450 pounds of high explosive. The first impact compromised the blister. More torpedoes followed in the opening minutes, ripping away the bulge and then, with at least one later hit, breaching deeper into the ship. The physics of the disaster were dictated by the speed of the water intake. The ocean did not just leak in, it didn't just leak in, it poured into oil bunkers and void spaces in a violent, accelerating rush. This massive influx of weight on the port side shifted the ship's center of gravity violently to the left. The righting arm, the force that keeps a ship upright, collapsed. Within roughly 15 minutes, the Leviathan surrendered to torque and rolled. She rolled. As the ship rotated past 90 degrees, the massive tripod masts, the fire control towers, and the 5-inch guns slammed into the harbor floor. But the floor of Pearl Harbor is not concrete. It is a soft, deep layer of volcanic silt and organic muck. The superstructure didn't just hit the bottom, it didn't just strike the bottom, it bit into the soft harbor mud and held there, stubborn and deep. When the hull finally came to rest, it was inverted at an angle of 151.5 degrees. The bottom of the ship was now the roof, posing a sleek, rusted island of steel above the water, while the operational heart of the vessel was buried upside down in the dark. This was the strategic nightmare facing the Navy in early 1942. The Oklahoma was useless as a warship, but she was effective as a blockade. She lay dead in Berth F-5, one of the most valuable parking spots in the Pacific. To win the war, the Navy needed that berth back. But to clear the berth, they had to move a hull that weighed as much as the Brooklyn Bridge, which was currently glued to the seabed by millions of pounds of suction. The standard salvage procedure for a capsized ship is to cut it apart. You slice the hull into manageable 20-ton sections and lift them out piece by piece. But the Navy hesitated. Cutting up a battleship containing hundreds of entombed sailors was bad for morale. Furthermore, the sheer mass of the armor belt, roughly 13.5 inches at its thickest, would burn through cutting torches and diving time for years. They needed a faster, cleaner solution. They needed to rotate the ship back onto its keel. Captain F.H. Whitaker, the salvage superintendent, looked at the schematics and realized he was not looking at a naval problem. He was looking at a leverage problem. He proposed a plan that sounded insane to the brass. He wanted to use the principle of the parbuckle, the same technique used by 18th century sailors to roll barrels up a ramp. But instead of a wooden barrel, he was trying to rotate a structure that was 583 feet long. The math required was staggering. To pull the ship upright, Whitaker calculated that he would need to generate a rotational force that exceeded the resistance of the mud, the weight of the water inside the hull, and the dead weight of the steel itself. The initial calculations suggested he would need 21 massive winches pulling simultaneously. But there was a catch. The winches needed to pull with such extreme tension that the cables would be stretched to their physical breaking point. If the ship stuck in the mud, if that suction seal didn't break instantly, the cables would snap. A 1-inch wire rope parting under heavy load becomes a lethal whip. Whitaker wasn't just planning a lift, he was planning a high-stakes tug-of-war with the physics of the Earth itself, about 0.1%, around 1,000 parts per million. That's the kind of hydrogen sulfide concentration that can stop breathing fast. Inside the overturned hull of the Oklahoma, the levels could spike higher. Before the engineers could even think about rotating the ship, they had to understand the environment they were working in. This was not a standard salvage operation where divers swam around a clean wreck. This was biological warfare fought in the dark. The interior of the ship was a decomposing slurry of paper, bedding, food stores, and hundreds of thousands of gallons of fuel oil mixed with the remains of the crew. When the salvage divers descended into the inverted hull, They were entering a chemical weapon. The primary enemy was not the depth of the water, but the opacity of it. The water inside the hull was black, not dark blue, but black. A diver could hold a lamp against the glass faceplate of his Mark V helmet and see almost nothing. They had to memorize the blueprints of a Nevada-class battleship and navigate entirely by touch. They crawled through upside-down corridors, sliding their heavy canvas gloves along steel bulkheads, searching for the jagged edges of torpedo holes. Their mission was strictly mathematical. To rotate the ship, Captain Whitaker needed to lighten the hull. The plan was to pump compressed air into the submerged chambers, pushing the water out and creating a bubble of buoyancy that would help lift the ship from the inside. This is a technique known as dewatering. But you cannot pressurize a sieve. The divers had to find hundreds of open portholes, hatches, and ventilation ducts that were now buried in the mud and seal them watertight. This led to the second, more formidable problem: soil mechanics. The superstructure of the Oklahoma acted like an anchor in soft bottom. Soil tests showed the stern would roll more easily, but the bow lay buried in soupy mud. To keep the ship from sliding, engineers even built up the bottom near the bow with dumped coral soil. Whitaker's team treated the bottom grip as a structural problem, not just a pulling problem. They equalized the loads with strain gauges, and they planned every step to make the hull roll, not slide, without overstressing the ship's own strength. To mitigate this, the engineers had to reduce the friction. They began a process of jetting. Divers hauled high-pressure water hoses down to the seabed. They used high-pressure water jets to wash away soil and jet out mud around the hull, loosening what the bottom was holding and clearing the way for movement. It was brutal, deafening work. A diver would be buried up to his waist in shifting silt, holding a hose that kicked like a shotgun while working underneath a 30,000-ton ceiling of unstable steel. And then there was the ordnance. Deep inside the wreck were the magazine spaces, oil-smeared, cramped, and still lined with heavy powder tanks. Every movement had to respect what those compartments were built to hold. A diver moving through the wreckage in heavy lead-weighted boots had to step carefully. One mistake in a confined space like that could kill you before you even knew what you touched. The danger was real, and it lived in the darkness, the oil, and the ordnance that had not forgiven the ship for capsizing. By early 1943, the righting plan was no longer theory. Oil had been pumped out, air pressure was used to blow the water level down inside the hull, and the bottom itself had been engineered, tested, and reshaped so the ship would roll instead of slide. Now the wreck was poised, heavy and unstable, waiting for the pull to begin. But the physics of the parbuckle required more than just buoyancy. It required torque. Massive, industrial-scale torque. The Navy looked at its inventory and realized it did not have enough heavy winches on hand to generate the necessary pull. They needed 21 hauling engines, synchronized, built to apply controlled force again and again over a long campaign of pulls. The solution would not come from the naval shipyards, it would come from the scrapyards of the city of Honolulu. The solution to lifting a 30,000-ton battleship did not come from the Pentagon. It came from Honolulu's retired streetcars. By 1942, Honolulu's electric streetcars had already been retired, replaced the year before by trackless trolleys and buses. This left a surplus of heavy-duty, direct-current electric motors sitting in storage. Captain Whitaker realized that the specific torque characteristics of a streetcar motor, designed to accelerate a heavy steel carriage from a dead stop, were exactly what was needed to break the suction of the Oklahoma. The Navy acquired the motors. On the shore of Ford Island, parallel to the wreck, engineers poured massive concrete foundations. This was not a temporary camp, it was an industrial installation. They mounted 21 electric winches, anchored in concrete, and fed them with the muscle of streetcar engines. Some were fitted for maximum pull at near zero speed. Speed was irrelevant. The goal was massive, sustained pulling power. The gearing and torque converters turned high-speed motors into slow, maximum pull at near zero speed. But a winch is useless without leverage. If the engineers had simply attached cables to the side of the ship and pulled, they would have only dragged the hull sideways through the mud. They needed to induce rotation. They needed to turn the hull into a rolling wheel. To achieve this, the salvage team constructed 21 giant triangular structures known as bents. These were essentially 40-foot-high A-frames, heavy timber structures mounted onto the exposed starboard bilge of the overturned ship. The physics here is identical to using a wrench to turn a stubborn bolt. If you push the bolt with your finger, it won't move. But if you put a long wrench on it and push the handle, the torque multiplies. The bents served as the handle of the wrench. The rigging plan was a masterpiece of geometry. 1-inch steel cables ran from the winches on the shore, out across the water, and up to the top of the wooden bents. From there, the pull was transferred through tackle blocks and pendants to the tips of the A-frames and into reinforced attachments and thrust brackets on the hull. This arrangement meant that when the winches pulled, the force was applied high above the center of rotation. It would pull the ship over rather than dragging it along. The scale of the rigging was dizzying. Tens of miles of 1-inch wire rope were reeved through the tackle system. To further increase the power, the engineers utilized a block and tackle system. By looping the cable back and forth between the shore and the ship multiple times, they created a mechanical advantage. For every foot of cable the winches retracted, the ship would move only a fraction of an inch, but the force applied would be multiplied 17 times. This was the streetcar solution. It was a hybrid monster of civil engineering and naval desperation. On one side, you had the raw, silent mass of a dead battleship buried in the mud. On the other side, you had 21 electric winches anchored in concrete foundations. Connecting them was a web of tension that looked like a suspension bridge lying on its side. However, a new danger emerged as the installation neared completion: the harbor bottom beneath her bow. The engineers realized that as the ship rolled right side up, the bilge keel, the long fin along the turn of her hull, would bite into the harbor floor. If the floor was soft mud, the ship would just slide and sink deeper. They needed a hard pivot point. Divers were sent down again, this time to build a tow. They dumped about 2,200 tons of coral soil near the bow, building a hard stop to keep the hull from sliding. They were essentially building a doorstop underwater. This bank of coral would catch the edge of the ship and force it to roll, acting as the fulcrum for their massive lever. By early March 1943, the machine was ready. The 21 winches were wired. Miles of 1-inch wire cable were tensioned through the block system. The wooden bents stood like a row of rib bones along the hull. The switch was about to be thrown, but the engineers knew that the initial application of power was the most dangerous moment. The static friction of the mud was an unknown variable. If the math was off by even 10%, the streetcar motors would burn out, or the cables would explode, decapitating anyone standing on the Ford Island shoreline. A massive electrical load. That was what hit Ford Island on the morning of March 8, 1943. The operation to right the USS Oklahoma did not begin with a roar. It began with a hum. The 21 electric winches, geared down for maximum pull, began to work in unison. On the shore, the winch drums rotated imperceptibly slow, taking up the slack in the miles of steel wire cable. For the first few hours, nothing happened. To the naked eye, the battleship remained a fixed, dead island of rust. But in the world of physics, a violent battle was taking place. This was the war between tension and static friction. The cables tightened. As the slack disappeared, the wire ropes lifted out of the water, shedding droplets of harbor slime, and became straight, rigid lines connecting the island to the ship. They were vibrating. Under the immense load, the steel began to elastically stretch, storing energy in the line. The cables were elongating, storing potential energy like giant rubber bands. If a single cable snapped now, the recoil could lash back with lethal force, turning the shoreline into a snap-back zone. The engineers watched the strain gauges. The load was climbing toward the wire's safe limit. The streetcar motors were whining, straining against the resistance. The mud suction was holding the ship down with an immense, calculated grip. The hull was not just sitting on the bottom, it was fused to it. Then, the geometry of the situation began to twist the ship. Literally. Across a hull 583 feet long, the resistance was not uniform. One end began to give before the other. As the winches pulled, the back of the ship began to lift while the front remained glued to the seabed. The battleship began to twist along its longitudinal axis like a wet dish rag. This was the critical danger. A battleship is a rigid girder designed to float on water, not to be torque-twisted by cables. If the twist grew too large, joints could start to fail and the hull could lose the strength they needed to refloat her. Captain Whitaker had to play the winches like a piano. He adjusted the winch schedule, shifting the load from one end of the hull to the other to keep the roll under control. It was a delicate, high-stakes balancing act performed with heavy industrial machinery. They were trying to coax the bow out of the mud without snapping the spine of the ship. Suddenly, the physics shifted. At last, the bow began to break free from the mud's grip. It didn't happen smoothly. It wasn't smooth. The breakout was violent. Mud and trapped air churned up around the hull as she lurched, and the cable surged, slacking and snapping tight again in seconds. The Oklahoma was moving, but the movement revealed a new, invisible enemy. As the ship climbed toward the upright, the wooden bents began to lose leverage. Around 68 degrees of list, the head frames were cast off and floated clear. These structures were designed to do one thing: push. But as the ship rotated, gravity began to take over. The bents were now hanging off the side of the ship, threatening to tear loose from their bolts. The engineers had planned for it. Once the bents stopped helping, they would be cast off to float clear, and the pull would shift directly onto the hull. The operation entered the zone of silence. The mechanical advantage was shifting. The block system's 17-to-1 advantage was about to matter less as the pull shifted away from the head frames and onto the hull itself. The motors were running hot. The cables were singing a high-pitched note of lethal tension. And deep inside the ship, the sound of water shifting inside the ship warned that stability was changing, and every adjustment had to be measured. 17-to-1. This ratio was the governing god of the operation. By routing the steel cables through a complex system of pulleys, blocks, and tackle, the engineers were trading distance for force. For the winches on Ford Island to pull the massive hull just 1 foot, they had to reel in 17 feet of wire. It was a trade-off that turned the high-speed spinning of the streetcar motors into a slow, unstoppable geologic force. The rotation of the USS Oklahoma was not a spectacle of speed. It was a spectacle of inevitability. Following the initial breakout from the mud, the movement settled into a grinding, agonizing crawl. The engineers controlled the roll in small increments, stopping when the strain gauges demanded it. This was not caution, it was survival. If the ship rotated too fast, the momentum of 30,000 tons of water-filled steel would become uncontrollable. If the roll ran away, the momentum could overwhelm the rigging and the whole system could fail at once. As the weeks of March and April 1943 ground on, the ship began to rise from the dead. The visual was grotesque. The first things to break the surface were the barnacle-encrusted undersides of the starboard bilge keel. Then came the armor belt, stripped of paint and gray with corrosion. But the true horror was revealed when the superstructure finally breached the waterline. The upper works had been ground into the harbor bottom since the day she capsized, and the mud did not want to let go. As the winches hauled her upright, the harbor floor refused to let go. Contact with the bottom had broken off the masts and much of the superstructure, leaving twisted stumps and wreckage to clear. They were twisted, bent, and packed solid with black clay. The decks were draped in a shroud of rotting nets, oil-soaked debris, and the crushed remains of the ship's launches. The wooden bents, the 21 massive A-frames that had provided the initial leverage, had served their purpose. As the ship climbed toward the upright, the geometry of the lift changed. Around 68 degrees of list, the head frames were cast off to float clear. The bents became dead weight. The salvage crews had to disconnect the cables from the high leverage points and re-rig them directly to the hull. This was the moment of maximum vulnerability. Without the leverage of the A-frames, the strain on the winches increased exponentially. The streetcar motors hummed at a pitch that suggested imminent failure. But the coral toe held. The fulcrum worked. By June 16, 1943, the righting was complete. The hull was considered upright. The operation had been a masterpiece of theoretical physics applied to heavy industry. They had taken a capsized battleship and flipped it over using nothing but electric motors and geometry. However, the victory was hollow. The ship that sat before them was not a warship. It was a ruined, toxic husk. The superstructure was crushed almost flat. The interior was a chaos of twisted bulkheads and oil sludge. And crucially, she was still sinking. The only reason the Oklahoma was not underwater was that she was sitting on the bottom of the harbor. The main deck was awash, and the hull was full of water. To actually refloat her, to make her buoyant again, required a new phase of engineering. The salvage teams had to seal the ship. This meant divers had to go back into the dark, navigating the upright but shattered interior to patch thousands of holes. They poured hundreds of tons of concrete into the bilges to seal the leaks. They installed massive cofferdam patches along the hull, sealing major damage and raising a working barrier above the waterline so the ship could be pumped down. Over the next months, the pumps roared to life. Vast quantities of water were driven out of the hull. By early November 1943, the Oklahoma lifted off the harbor floor. She floated. The salvage of the USS Oklahoma was officially a success. It was one of the greatest feats of marine engineering in history. But as the Navy surveyed the resurrected hull, they came to a cold realization. The structural damage was total. The cost to repair her would exceed the cost of building a new battleship. The Oklahoma had been saved, but she had no future. She was a zombie ship, resurrected only to be discarded. And the ocean, it seemed, was not done with her yet. The physics of her final voyage would prove to be even more mysterious than her salvage. The irony of the USS Oklahoma is that the greatest engineering feat of the Pacific War was performed on a corpse. After 2 years of labor, millions of dollars, and the invention of entirely new salvage techniques, the Navy looked at the resurrected battleship and made a cold calculation. She was too old. She was too damaged. The cost to modernize her systems would have been ruinous, far beyond what the Navy was willing to spend. The massive parbuckling operation, the streetcar motors, the heroic diving, it had all been done not to save the ship, but to clear the parking space. On September 1st, 1944, the Oklahoma was decommissioned. Stripped of guns and superstructure, she was sold on December 5th, 1946, to Moore Dry Dock Company in Oakland, California, for about $46,000. The mighty battleship was destined to be melted down into razor blades and girders for post-war skyscrapers. But the Oklahoma had one final act of defiance left. In early May 1947, 2 ocean-going tugs, the Hercules and the Monarch, arrived at Pearl Harbor. They rigged a heavy tow line to the bow of the battleship. The Oklahoma was now a dead ship. She had no engines, no rudder, no electricity, and no crew. She was simply a hollow steel geometry displacing water. The plan was to tow her more than 2,000 miles to a breaker's yard in San Francisco Bay. For the first week, the tow was uneventful. But on May 17th, more than 500 miles from Hawaii, the ocean turned hostile. A storm hit the convoy. The seas built fast. The Oklahoma, lightened by the removal of her armor and guns, rode high in the water. But without a crew to manage her ballast or seal leaks, she was vulnerable. As the storm intensified, the tug captains noticed something terrifying. The searchlights from the Hercules swept back across the heaving black water and found nothing. The Oklahoma was not riding the waves, she was listing. She had begun to take on water, for reasons never firmly established, and the list kept growing. The stress of the open ocean was reopening the wounds of Pearl Harbor. Then the geometry shifted from towing to anchoring. The Oklahoma began to sink. But she didn't sink straight down. She pitched violently. The weight of the water rushing into her hull transformed her from a floating vessel into a tens of thousands of tons counterweight plunging into the abyss. The tug Hercules was tethered to this dying leviathan by a heavy steel tow line. As the Oklahoma dove, she pulled the cable tight. The Hercules, a powerful vessel in her own right, stopped moving forward. Then she started moving backward. The sinking battleship was dragging the tugboat down with her. The physics were simple and lethal. The kinetic energy of the plunging battleship vastly exceeded the horsepower of the tug's engines. The Hercules was being winched into the deep by the grave she was towing. The crew of the Hercules scrambled to the stern. The winch drum was screaming, the brake smoking as the wire paid out. If they couldn't release the tension, the tug would be pulled under stern first in seconds. The captain ordered the emergency release. The brake was tripped. The cable tore off the drum in a violent scream of steel, disappearing into the foaming water. The Monarch, seeing the disaster, also cast off her lines. Freed from her tethers, the USS Oklahoma did not linger. She did not capsize slowly as she had in 1941. She plunged straight down, returning to the crushing pressure she had known for so long. She sank rapidly, dropping into the Pacific thousands of feet down. She was never seen again. Her exact final resting place remains unknown. The salvage of the Oklahoma was technically a success, but spiritually it was a strange loop. The Navy spent years fighting physics to bring her to the surface, only for her to fight physics to return to the sea. She evaded the blowtorches of the scrapyard and vanished again in a storm more than 500 miles from Hawaii. Her exact resting place remains unknown. The true legacy of the operation was not the metal saved, but the knowledge gained. The parbuckling system under Captain Whitaker, 21 hauling winches, 1-inch wire, and a 17-part purchase, pushed the limits of marine salvage. And when the Navy later revisited the question of the USS Utah, the shadow of Oklahoma still hung over the plans. She was a ship that died twice, but the engineering used to resurrect her is immortal.